Hello everyone, so today we're going to go over section 7.2, transformations of sinusoidal functions. So with periodic function, a vertical translation is called a vertical displacement, and a horizontal translation is called a phase shift. So in our example 1, we are looking at a function y equals to sine x minus 30 degrees plus 1. So we have a phase shift of 30 degrees to the right and 1 unit up. In order to sketch this graph, we'll be using the function y equals to sine x, which is already drawn on the grid. So a good way to think about this transformation is to think about it in terms of the center or midline of the graph. Originally, with y equals sine x, the midline is just the x-axis. But since the function is being moved up one space, the new midline is going to be y equals 1, or the new center line. Secondly, we know that the graph is moved 30 degrees to the right, which using this grid is 1 square to the right. So each squared here is 30 degrees. So our new graph is going to start at this point here, 30 degrees to the right and 1 unit up compared to the original point. And we can translate all the rest of the points of the graph in a similar fashion. So every point is moved 1 square to the right and 1 unit up. So 2 squares up in this case. Just one more example here. Again, 1 square to the right, 2 squares up for 30 degrees to the right and 1 unit up respectively. So once that's done, we can connect the points together with a smooth curve, like so here. And that would be sufficient for the sketch of this function for at least one cycle. Information about this function, y equals to sine x minus 30 degrees plus 1. Again, the vertical displacement was plus 1 or 1 up. The phase shift was 30 degrees to the right. Now the period is unchanged, so it will still be 360 degrees, one full rotation. The domain x is an element of the real numbers. The amplitude is also unchanged, so that is just going to be 1. And finally, the range is now changed from 0 to 2. Like so. Inclusive, of course. Now, let's look at a second example with cosine. And a few key differences here. For example, we have radian instead of degrees. We also have an additional vertical stretch and reflection. So as always, we'll begin by listing the transformation that happens. There's a reflection over the x-axis. Okay, there's a vertical stretch by 2. The graph is translated pi units to the left. And 1 unit down. Okay, so we can begin with any one of these points on the graph. So for example, 0, 1, and just take it through the transformation. So we'll start with 0, 1. It'll be reflected over the x-axis, so it'll become 0, negative 1, then vertically expanded by a factor of 2, so that takes us to 0, 2. And then the whole point will move pi units to the left, so we'll end up at negative pi, negative 2, and finally 1 unit down. So it's going to end at negative pi, negative 3. So of course, one way to draw this graph is to transform each one of the points in that manner. But it's probably easier to focus on the key points at the beginning, the end, the halfway point, and the first and third quarter of the graph. And only transform those points. So let's look at the second point in our sequence that we just described. The first quarter point, so this will be pi over 2, 0. So when it's reflected over the x-axis and vertically expanded by 2, that doesn't change the point because the y-coordinate was originally 0. We'll then move it to the left pi spaces, so it will be at negative pi over 2, and then down 1 space. So it's going to end up at negative pi over 2, negative 1. Similar to the third point here, here is going to be reflected, vertically expanded, and then move to the left, and then down 1 space. So it's going to end up at 0, 1. Next point we have is the third quarter mark. So that's 3 pi over 2. Again, the reflection and the vertical stretch will not change the point. The translation horizontally will, and also the vertical translation down 1 space. So it's going to end up here. And finally, last point at 2 pi, reflected, vertically stretched, move left by pi, and then down 1 space. It's going to end up here. Okay. So those 5 points will be sufficient to produce the graph. It would be better to include these additional points at the 1/2 and negative 1/2 y value respectively and transform those as well. If we were to do that, this is where they would end up. And once again, we were to connect all the points to make a smooth curve. So something that looks like this. So once the graph is produced, we can check it to see that it is done correctly. The graph is upside down, so that's good. Is twice as tall as the original function, so that vertical stretch by 2 was applied correctly. The graph starts at negative pi instead of 0, so the translation, the phase shift was done correctly, and also the graph, the center line was moved down 1 space. So a good way to keep track of the vertical displacement is to see where the midline becomes. Originally, for y equals to cosine x, the midline was at y equals 0. So the new midline being at y equals negative 1, that makes the most sense. And in fact, it is correct. So now let's look at the properties of this graph. We already have that the vertical displacement was 1 down. Okay, the phase shift was pi to the left. The period remains unchanged, so this is going to be 2 pi. The domain x is an element of the real numbers. The amplitude, because of the vertical stretch, is now 2. And the range is going to be from negative 3 to positive 1. Okay, so in the next example, we're going to combine the three transformation that we have seen, the stretch and the translation, both horizontal and vertical, and also a change in the period. So we have the function y equals sine x, and then we are to graph y equals to 3 sine 2x minus 2 pi over 3 plus 2. So just as before, the first thing we're going to do here is factor out the 2, like so. So we have y is equal to 3 sine, and then in parentheses 2, and then parentheses again, x minus pi over 3, close parentheses, plus 2. Okay, doing so will allow us to treat the translations at the end, which is what we usually like to do. So transformations, again, in order, this is a vertical stretch by 3. This is a horizontal stretch by 1/2. And then the graph will be translated pi over 3 to the right, or phase shift of pi over 3 to the right, and a vertical displacement 2 spaces up. Okay. So in this case, we know that the new period is going to be 2 pi over 2, which is going to be pi, which is different from the previous two examples. So let's see how we can graph this. Again, it would be easier if we focus on the key points. So again, the start, the end, the quarters, and then the middle point. So let's start with the starting point of 0, 0. It will not be affected by the vertical and the horizontal stretch, so it will remain at 0, 0. So the only transformation that's going to move the point is going to be the two translations. So pi over 3 to the right. So starting here is going to be pi over 3 to the right, which ends up here, and then 2 spaces up. So this is going to be our new starting point here. Now, we know that the period is pi for the new function, and pi is 6 spaces wide on this graph. So this is the beginning, and we all know already that 1, 2, 3, 4, 5, 6, that the graph is going to end at this spot because the period is pi. Now, halfway through the function, at the middle of the period, we have another 0 or another midpoint. So it's going to be there. So the point pi 0 will be transformed to 5 pi over 6, 2, if we were to follow all the steps in transforming the point. What we also know is that at the first quarter, the graph reaches its maximum, and this maximum is going to be 3 spaces above the midline, which we established through the first 3 points. That it is here. Also by the fact that the vertical displacement is 2 spaces up. So this is y equals 2, and that's the new midline. We already have the first 3 points on there. Translated pi over 3 to the right, this point was, and then move 2 spaces up. And then we use the fact that we have a period of pi to construct these 2 additional points. So all we are left with is the maximum point and the minimum point of the period. The maximum point is going to be 3 spaces above the midline, and it's going to be halfway between the start and the first half of the function, of the period, sorry. And then here, the second point will be halfway between, again, the halfway point and the end. It's going to be 3 spaces down. So a good idea to draw or to make a sketch of such functions is to use the method that we just described here. And how it works is we use the transformation to find a starting point, like we did here. We use the period to find the end point, and then use the quarters system, if you will, to find the rest of the points. Rather than making a table of values and transforming the points individually, which will also work, but usually that would take much longer, and it's easier to make mistakes that way at times. Okay, so again, just to reiterate, this starting point, we'll call these points A, B, C, D, and E. And these 5 points are A prime, B prime, C prime, D prime, and finally E prime to produce the new graph. Okay. So with all that in mind, let's look at the properties of this graph. We have the vertical displacement of 2 up, the phase shift of pi over 3 to the right, the period is pi, and the reason for that is because 2 pi divided by b, which is 2, is equal to pi. The domain is x is an element of the real numbers. The amplitude is 3 because of the a value. And finally the range is from -1 all the way up to 5. Which makes sense because the usual sine function will span 2 spaces from -1 to 1. And when we triple the, when we have a vertical stretch by 3, the range will be triple the size. So from -1 to 5 is 6 spaces, which makes sense. Okay, so next one, example 4, is another element that's important, and that is a change in the period so that it is no longer in terms of pi. But before that, let's just list out the transformation once again from left to right. Notice this time around the pi over 6 is already factored out of the x plus 3. So starting from left to right, we have a reflection over the x-axis. So the graph will be upside down. There's a vertical stretch by a factor of 2, so it's going to be twice as tall. Now, this next part is tricky because this is actually a horizontal stretch by 6 over pi, the reciprocal of pi over 6. From there, the graph is moved left 3 spaces, or 3 left, and 1 down. So the challenge here is because the new period is not in terms of pi, it doesn't make sense to base our graph on the original y equals to cosine x function because that function is constructed in terms of pi. So what we're going to do instead is to consider what the new period is. So the new period is going to be equal to 2 pi divided by the b value, which is pi over 6, which of course is equal to 12. So the period is 12. Which means what we can do is first graph y equals to cosine pi over 6x. Okay, so again, we'll construct this graph using the start to end and then the quarters. So the cosine function starts at 0, 1. It starts at the maximum, and it's going to end at the maximum as well. At the halfway point of the cosine function, it reaches its minimum value. So at x equals 6, we'll have -1. We can also confirm that by substituting 6 into the y equals cosine pi over 6 function. The 6's eliminate each other, so we're just evaluating cosine pi, which is a -1. From there, we can also find that from the first quarter, we have a 0, so we have 3, 0 for the function that we're graphing right now, and then also 9, 0. Okay, so we can also add some additional points to make it easier to draw. But overall, this is going to be our base function, in this case, y equals to the cosine pi over 6x. And that is how we can utilize the different quarters and the start and the end of a cosine function. So again, a cosine function starts at the maximum value if it's positive, and then in the first quarter it is at 0, at the halfway point is at the minimum value, at the third quarter is at 0 again, and finally at the end it reaches the maximum again. Okay, so this is our y equals to cosine pi over 6x function, which means now all we need to do is to take care of the reflection, the vertical stretch, and then the two translations. Okay, let's consider this first point here, 0, 1. So the point 0, 1 is going to be reflected to 0, negative 1. It will be expanded to 0, negative 2, and then move 3 spaces to the left, and then 1 more space down. So it's actually going to end up at negative 3, negative 3. Let's go ahead and draw that in. So this is our starting point. Now, we already know that the period is 12, so the function is going to start here and end at x equals 9. Okay, so one additional detail that will be useful here is the fact that the original function, in this case y equals cosine pi over 6x, has a midline of y equals 0, and the new function will have a midline of y equals negative 1 because of the vertical displacement. So let's add that in. So this will be the midline of the function that we're trying to graph right now. At this point, we can use the beginning and end points, and then use the first and third quarter and then the halfway point to construct the rest of this graph. Okay, at the halfway point between negative 3 and 9, we have positive 3. And at x equals positive 3, we will have the minimum point of the period, but it's upside down, so it's actually going to be the maximum point, and it's going to be up at 3, 1. Alternatively, we can just take the point 6, negative 1 and apply the transformations. We'll end up with the same thing, so let's try it here. So we have 6, negative 1, reflected is 6, positive 1, and then vertically stretched by 2 is 6, positive 2, and then left 3 spaces is 3, 2, and then down 1 is 3, 1. So we end up at the same point, transforming the points individually or using the coordinate system that we have. So at and then the first quarter between negative 3 and 9, we'll have 0. And at the first quarter, we'll have our the graph will intersect the midline, and also at the third quarter over to the right hand side. And so from there, we can also construct some additional guiding points to complete the graph. Although they're not completely necessary, it's just easier to draw a cosine function if we have them. They're not completely necessary, and they would be easy to find too. We can just transform points like 8, negative 1/2 to the new location to have some additional points for sketching this graph. Anyways, so again, let's just review that we did everything correctly. The graph should be reflected over the x-axis, so the final product should be upside down. It is. It should be vertically stretched by 2, so we can see that the original function spanned 2 spaces, now it spans 4 spaces. That's correct. It has the right period of 12, from negative 3 to positive 9. The graph was moved 3 spaces to the left from the original, and the midline was moved down 1 space. So all of that seems correct. After that, we can simply, again, list the transformation that happened. The displacement was 1 down. The phase shift was 3 to the left. The period is 12 spaces. The domain x is an element of the real numbers. The amplitude is 2. And finally, the range is from -3 to +1. Okay. So one more topic to cover here, and that is the writing of the sinusoidal functions based on the transformation that we have seen before. So we have the 4 variables a, b, c, and d. A, as before, is responsible for the vertical stretch, or the amplitude in this case. The b value is about the horizontal stretch, or the period. So notice that b is equal to 2 pi over p if it is in radian. If this is in degree, that would be 360 degrees divided by p. C is the starting point, or the phase shift of the function that we're dealing with. And finally, D is the midline of the vertical displacement. Okay. This formula here, or this equation here, is an easy way to find out what the amplitude is. Simply subtract the maximum and minimum values of y and divide it by 2. Okay, so what if we are given the graph of a sinusoidal function and asked to find its equation? So, well, we'll start with the easy parts. In this case, we can see the midline. It's right here at y equals 2. So because the midline is at y equals 2, we can already tell that the vertical displacement must be 2. So in other words, the d value is equal to 2. Next is the amplitude. So the amplitude, again, is from the midline to the maximum or the minimum values. Those will be the same. And because we're looking at distances, amplitude should always be positive. So in this case, the amplitude is just 2. And that is to say that the absolute value of A is 2. Next up is the period. So one way to examine the period is to look at the distance between consecutive maximums. So something like this here. And we can see that one period goes from pi over 3 to pi, which means the period is actually 2 pi over 3. So we have period is equal to 2 pi over 3, which means we can calculate the b value, and that's going to be 2 pi over 2 pi over 3, which means the b value is just 3. Notice that we did not look at or consider the c value, the one that controls the phase shift of the graph, because the type of function, that is to say, the type of trigonometric function we're working with will determine what the phase shift needs to be. Okay, in this first example, part A, we're looking at a positive sine function because A is greater than 0. So we already know a few bits of information. We know that the A value is going to be 2, positive 2 in fact, because the function is positive. And then we have sine, and then this will be 3, and then x minus, we don't know that number yet, and then plus 2 at the end. So what we know about the sine function is that it needs to start at the midline and then immediately move upwards. That's the shape of the graph in general. So we need to look for somewhere on this graph where that happens. If we consider this point, for example, pi over 6, 2, notice that it starts at the midline and then immediately moves upward. So that's a possible choice for our c value. Likewise, we can also choose this point as well. That will also work because, again, we start a midline and it immediately moves upwards. And we have other choices as well. So the choice is not unique, but of course there is a set criteria as to what we can choose for the C value. Again, this is going to be pi over 6. Next up, we have the positive cosine function. So kind of similar in some ways, because we again have a is equal to 2. We have, cosine. The b value is still 3. Again, we have x minus c, and then plus 2. So what we need to know about the cosine function is that it starts at the maximum and then moves downwards. So we need to find where on this graph is the graph at the maximum. So pi over 3 is a possible choice. That is the maximum, or pi, or 5 pi over 3. Those are all possible starting points of the positive cosine function. But we'll choose the principal answer, and that is the one that's closest to the y-axis. So that would be pi over 3. Okay, next up is a bit of a tricky one, the negative sine function. The negative sine function will actually start at the midline and then move downwards. So that's negative 2 sine 3, and then x minus, and then we don't know yet, and then plus 2. Okay, so let's look at what we have here. In this case, if we have negative pi over 6, that point is at the midline and then it's moving downwards to the right. So that's a possible choice. So we can write this as negative 2 sine 3 and then x plus pi over 6 and then plus 2. And finally, the last one, the negative cosine function in example D, that has to start at the minimum. Notice that if the phase shift was 0, then the function is already starting at the minimum. So we can just write this as y equals to negative 2 cosine 3x and then plus 2 with no phase shift. And that is a useful fact for the word problems that we'll be examining in a later section in this unit. However, that's it for today, and so thank you for listening.